Hi, this is Rob. Welcome to this Cumulus Cycles AWS hands-on tutorial, where I'll show you how to provision AWS infrastructure using Terraform. In order to follow along, you'll need Terraform installed on your computer. I've created a video on how to install Terraform on a Mac, and I'll provide a link to it in the description below. Before we get started, let me just note that this tutorial is not intended to prepare you to take the HashiCorp Certified Terraform Associate exam. Although I will demonstrate several key concepts which are included in the exam domains, I highly recommend a course designed specifically for the exam, such as the HashiCorp Certified Terraform Associate course on A Cloud Guru. Before writing your Terraform templates, you should ensure that you have run AWS Configure and added the appropriate credentials for your IAM user. You should also grant the user permissions to the resources you'll be provisioning, or you can grant your user administrative access for simplicity, but you should always follow the principle of least privilege outside of a learning environment. To get started, I've launched VS Code, and I'll create a new source folder to hold the templates. Then inside the folder, I'll create a main.tf file, which will be our main Terraform template. Inside the main TF, I'll add the Terraform block and specify the required version and the AWS provider. And in the AWS provider, I'll specify the region of US East 1. Now, I'll jump over to my terminal, change the directory into the source folder, and run the Terraform init command to initialize the Terraform working directory. Now, I'll create a new modules folder inside of the source directory, and then add a folder named tfstate. Inside the tfstate folder, I'll create a main.tf file and add the Terraform block. Then I'll create a new file named tfstate.tf, which will be used to define the S3 bucket for the Terraform state file and a DynamoDB table, which will be used for locking the Terraform configuration. Here I've added a resource for an AWS S3 bucket, and the bucket property will be populated from a variable which we'll create shortly. I'll add versioning to the bucket and then enable server-side encryption. Finally, I'll add the resource for the DynamoDB table, then save the file. Now I'll create a variables.tf file and paste in the variable definition for the bucket name variable. Here I've given the variable description that this will be the remote S3 bucket name. Its type is a string, and I've added validation on the bucket name, and an error message which will be displayed if the bucket name is empty or doesn't follow the S3 naming rules. Now I'll jump back over to the main TF file and add a module for the TF state, which source points to the modules folder in the TF state folder. And here I'm setting the bucket name for the variable. Now I'll jump back into the terminal and run a Terraform format to format my code, then a Terraform init to install the new module, and a Terraform validate. With validation successful, I'll now execute a Terraform plan. And here we see the plan will add 4 resources: the DynamoDB table, the S3 bucket, and configure server-side encryption and bucket versioning. Now I'll go ahead and execute Terraform apply to provision the resources. Again, we see the plan is to add 4 resources. I'll go ahead and confirm. And with the apply complete and the 4 resources added, I'll jump over to the AWS console and refresh the S3 buckets, and we see our new Terraform state backend bucket created. Then I'll jump over to DynamoDB, and we see the new Terraform state locking table. Now, by default, Terraform is using a local backend to manage the state. However, I'd like it to use an S3 bucket for the backend. So I'll add the backend block, which sets the backend to S3, defines the bucket, sets a key, the region, and specifies the DynamoDB locking table, and finally sets encryption to true. So I'll save the file, jump back into the terminal, run Terraform init, and say yes to copy the new S3 state to the backend. Then run a Terraform apply to configure the backend on S3. I'll enter yes for the one change, and the backend is now configured on S3. Now, with the backend set, we can turn our attention to defining our AWS infrastructure, and we'll start with building out the VPC. So I'll jump back over into VS Code and create a new VPC folder in the modules directory. I'll add a main.tf file, paste in the Terraform block, then create a vpc.tf file. And here I'll define the resource for an AWS VPC. The CIDR block will be provided via a variable, the instance tenancy will be default, and I've given it name and project tags. We'll need an internet gateway, so I'll define the resource block here. Its VPC ID property will be obtained from the AWS VPC CCVPC's ID, with the CCVPC defined in the resource block above. Because I want 2 NAT gateways, one in each public subnet, in the 2 availability zones, I'll paste in resource blocks for an AWS Elastic IP for NAT Gateway 1 and an AWS NAT Gateway for the first gateway. The first gateway's allocation ID will come from the AWS EIP NAT Gateway 1's ID property, and the subnet ID will come from the AWS subnet's public subnet 1 ID. Here I'll define an AWS subnet for the public subnet 1, set the VPC ID equal to the CCVPC's ID created above, and the CIDR blocks and availability zones will be provided by variables which we'll define later. Then I'll create the resources for NAT Gateways 2 EIP and NAT Gateway 2. And I'll add a resource for the AWS subnet for public subnet 2. Again, its VPC ID is set to the ID of the CCVPC, and the CIDR block and availability zones will be provided via variables. I'll also add resources for private subnet 1 and private subnet 2. Then I'll add AWS route tables for the public route table, private route table 1, and private route table 2. They'll all have VPC IDs obtained from the CCVPC ID. The CIDR blocks will be wide open, and the public route table's gateway ID will be obtained from the AWS Internet Gateway named CC Internet Gateway's ID property. The NAT Gateway ID for the private route table 1 will come from NAT Gateway 1's ID, and the NAT Gateway ID for private route table 2 will come from NAT Gateway 2's ID. Finally, I'll add AWS route table associations for the public and private subnets. And the subnet ID and route table ID properties will be set from the public subnet and public route table properties, and the private subnet and private route table properties. Now, inside the VPC folder, I'll create a variables.tf file and paste in the variable block for the VPC CIDR variable. Its type will be string, and its default value will be 10.0.0.0/16. I'll add a variable for the availability zones, which type will be a list of strings, as well as variables for the public and private subnet CIDRs. Finally, I'll add an outputs.tf file and add outputs for the VPC ID, whose value will come from the CC VPC ID property, the public subnets, whose value will be a list of strings obtained from the public subnet 1 and public subnet 2, and the private subnets, whose value will be a list of strings from private subnet 1 and private subnet 2. And if we look at the VPC TF file again, here we see the AWS VPC named CCVPC, which is where the CCVPC ID variable's value is obtained. Also, the AWS subnets for public subnet 1 and public subnet 2, as well as private subnet 1 and private subnet 2. Finally, we'll jump back over to the main TF file and paste in a module block for the VPC infra, whose source points to the VPC folder inside of the modules folder. We'll pass values for the input variables VPC CIDR, availability zones, and public and subnet CIDRs, which will come from local variables. And to set these values inside of the source folder, I'll create a new file named locals.tf. And then create the availability zones, which is the list of strings containing USDs to 1A and 1B, the VPC CIDR of 10.0.0.016, and the public and private subnet CIDRs. Now I'll jump back over to the terminal and run Terraform init to pick up the new module. Then I'll run Terraform validate. And finally, Terraform apply. I'll say yes to confirm the plan to add 18 resources. And after just about 5 minutes, we see our 18 resources have been created. So let's jump over into the AWS console, go over to VPCs, click into VPCs, and we see our new CC VPC has been created. We have our public and private subnets, our route tables, the internet gateway, the NAT gateways, all within our CC VPC. Now let's turn our attention to provisioning the RDS database in a private subnet. To get started, I'll create a DB folder in the modules directory, and then a main.tf file in the DB folder. I'll add the Terraform block, then create a db.tf file. In a db.tf file, I'll add a resource for an AWS DB subnet group and set the subnet IDs equal to a list which will be populated from variables we'll pass in. I'll then add an AWS security group and assign its VPC ID property equal to the CC VPC ID we'll pass in as a variable. We'll set the ingress ports in the protocol, and the CIDR blocks will be passed in as variables. And finally, I'll add a resource for an AWS DB instance. I'll pass the availability zone in through a variable. The DB subnet group name will be set from the AWS DB subnet group created above, named CCDB subnet group, and grabbing its name property. The VPC security group IDs will come from the DB security group's ID created above. I set the storage type to standard, the engine to Postgres, and an instance class of dbt2 micro. The name, username, and password properties will be passed in as variables, and I've set the skip final snapshot property to true. As with the other modules, I'll create a variables TF file and add variable blocks. I'll start with the private subnets, which will be a list, and the private subnet CIDRs, which will also be a list. The CC VPC ID will be a string and have validation with a condition that the length should be greater than 4 and a substring should start with VPC dash. The DBAZ will be a string with a validation condition which contains a regex pointing to the variable DBAZ. And finally, I'll add variables for the DB name, DB username, and DB password. These will all be strings with sensitive set to true. Jumping back over to the main TF, I'll add a module block for the DB infra, which will point to the DB folder in the modules directory. The VPC ID in private subnets will be obtained from the VPC infra module created above, referencing the resources. The private subnet CIDRs will come from the local variables. The DBAZ will also come from the local variables availability zones, and the DB username and passwords will be provided via variables. So I'll save all changes to the files, jump back into the terminal, and execute a Terraform init to pick up the new module. I'll run a Terraform validate, and in this case, we'll see we have a couple errors stating that there's a reference to undeclared input variables for the DB username and DB user password. So inside of the source folder, I'll create a new file for variables and add variables for the username and password. Then I'll jump back over to the terminal and run Terraform validate again. This time it looks good. So I'll run the Terraform plan. And here I'm prompted to enter the DB username, but I'll leave this blank and also leave the DB user password blank. And we'll see that I've failed input validation for the username and password. So this time I'll run it again, providing valid values for the username and password. And now that the plan looks good, I'll go ahead and run Terraform apply. And confirm the changes. And after a little over 4.5 minutes, we see our resources have been provisioned. So let's jump over to the AWS console, head over to RDS, click on databases, and we see our new database instance in the US East 1A availability zone inside of our VPC. Now, we're making really good progress here. We defined and provisioned our VPC and the RDS database. So what's left is to create the EC2 instances for the web servers. So jump back over into VS Code, and inside the modules folder, I'll create a new folder for the web servers. I'll start with the main TF file and a Terraform block, then create a web servers TF file. Inside the web servers TF file, I'll add a resource for an AWS security group. Its VPC ID property will come from a variable, and the ingress will be dynamically created using a for each for each ingress rule passed in as a variable. The from port, to port, protocol, and CIDR block properties will be set referencing the ingress's value for port, proto, and CIDR blocks. I've also set properties for the egress and added tags. Here I'll add a resource for an AWS load balancer. The load balancer type will be an application load balancer, and the subnets will be passed in as variables. The security groups will reference the AWS security group web server security group's ID property. The AWS Load Balancer Listener will have a Load Balancer ARN property which references the AWS LB's Load Balancer's ARN. The default action will have a target group name referencing the AWS Load Balancer target group's target group ID, and the type will be forward. Here I'll define the Load Balancer target group, set the port, protocol, and the VPC ID will be passed in as a variable, and define the properties for the health check. I'll add resources for target group attachments for Web Server 1 and Web Server 2, and set the target group's ARN to the target group's ARN property. The target ID for Web Server 1 will be AWS Instance Web Server 1's ID, and Web Server 2 will be set to AWS Instance Web Server 2 ID. Here I'll define an AWS Instance resource for Web Server 1. The AMI instance type and key names will come from local variables, and the subnet ID will be passed in as a variable. The security groups will reference the ID of the web server security group created above. I'm associating a public IP address and then defining user data. Finally, I'll add a resource block for Web Server 2 with similar properties, and in the user data, the server value will be set to Web Server 2, whereas in Web Server 1, the server value will be set to Web Server 1. Since I'm referencing local variables in the Terraform file, I'll need to create a locals TF file, and I'll add values for the AMI ID, instance type, and a key name. And just a note that the CCKP key will need to be created before we can provision the infrastructure. And if we jump over to the EC2 dashboard, we'll see I have one key pair for CCKP. Now I'll create a variables.tf file and add variable for the public subnets, the VPC ID, and the ingress rules, which is a list of objects with a port, a proto, and the CIDR blocks, with default values for the port, proto, and CIDRs for port 80 and port 22. And if we go back to the web server's TS file and look at the AWS security group resource, this is where the ingress rules variable is referenced in the for each loop. Finally, I'll add an outputs TF file and add an output for the load balancer's DNS name, which will reference the AWS LB load balancer's DNS name property. Now I'll jump over to main TF and add a module for the web server infra pointing to the web server folder in the modules folder. The VPC ID will be set from the VPC infra modules CCVPC ID, and the subnets will also come from the VPC infra module, and that will reference the CC public subnets. So now I'll jump back into the terminal, run a Terraform init to pick up the new module, run a Terraform validate, and then a Terraform apply. I'll enter yes to add the 9 new resources. And here I'll pause the video until the resource creation is complete. So it took just under 3 minutes to provision the resources. And if we jump over to the AWS console and refresh the EC2 dashboard, we'll see we have 2 running EC2 instances. I'll jump into the first one, which is in the CCVPC, grab the public IP, and load it in a browser tab. And we see we're on Web Server 1. Then I'll jump back and grab the other IP address, put that in a browser tab, and we see we're on Web Server 2. So now let's go back to the EC2 console, and we see our target group, which is attached to our load balancer. It has the two targets, which are healthy. And if we hit the load balancer and grab the DNS name and load it in the browser, we'll see we're on web server 1. And if we refresh, now we're on web server 2. Finally, I'll issue a Terraform destroy to tear down the infrastructure. So that concludes this video on provisioning AWS infrastructure using Terraform. If you found this informative, feel free to give it a thumbs up. And if you'd like to be notified when I release new content, please consider subscribing to the channel. Thanks for watching.